Trace32 debug support for Unified UEFI bootloader. Trace32 offers a loadable extension to its JDAG debuggers for Intel x86, x64 and Cortex-A that allows a comprehensive debugging of UEFI BIOS systems. This capability eases and supports the development of all UEFI phases and components with special windows and UEFI-aware menus. You can start your debugging right from the reset vector and step through all parts and drivers up until the handover to the OS or even into the OS if required. Trace32 is aware of multi-core environments, allowing UEFI debugging even on SMP systems. The Trace32 UEFI extension is currently supported for the following UEFI versions. We use in this video a Trace32 PowerView for Intel x86 64-bit release of February 2080 with a PowerDebug Pro and a Combi Prop connected to a MenuMax board which has an Intel Atom E3825 processor running the Intel Bootloader Development Kit BLDK. I use the following practice script to connect to the target processor and configure the UEFI-aware debugging. Key for the Trace32 UEFI debugging is that the Trace32 BLDK awareness is loaded during this setup. The BLDK awareness is an extension that Lauterbach provides for its debuggers. Furthermore, the startup script adds a new BLDK menu to the Trace32 PowerView, which includes menu useful items to ease UEFI debugging. I will start the script by pushing the Continue button. The processor has been reset by the debugger and stopped at the reset sector. I will show in the following how to debug through the pre-UEFI initialization phase, the DXE phase, and finally the BDS phase. We will see how the PI core is copied to RAM and how DXE drivers can be debugged using few mouse clicks. But let me first give you some information about the so-called Trace32 symbol autoloader, which is a basic component of UEFI debugging in Trace32. The symbol autoloader is a Trace32 feature that can be set up for automatic loading of debug symbol files. With the help of the Trace32 BLDK awareness, the autoloader checks the currently available UEFI modules. The autoloader maintains a list of address ranges, corresponding UEFI components, and the appropriate load command. Whenever the user accesses an address within an address range known to the autoloader, the debugger invokes the load associated command. The user can additionally trigger the loading of debug symbols for selecting modules manually per mouse click or from a script using an appropriate Trace32 command. The debug symbols for the PEI core can be loaded simply by doing a right mouse click on the module name and select Touch. We can now browse the loaded debug symbols by selecting the Trace32 menu View, Symbols, Browse Functions. I will search for instance for the PEI core function and set an on-chip breakpoint there because the code is running out of the boot flash. Let's resume the program execution. We are now in the pre-UEFI initialization phase. The execution is stopped at the entry of the PEI core function, which is currently executing from the flash. We can display the list of PEI modules using the menu BLDK, PEI, Display PEI modules. The PEI core will be copied later into RAM. I will set a breakpoint at the following location and restart the execution. When we stop at the breakpoint, we see that a second PEI core entry has been added to PEI module list with its addresses in the RAM. The execution will jump after some assembly instructions to the start address of this module. We can now reload the symbols for the PEI core by simply selecting the menu BLDK, then load current symbols. Now the code is completely copied from the boot flash to RAM. Consequently, we have to update our module list. We can see that the DXC core entry has been added to the autoloader list. We can simply load the symbols of this module as shown previously by doing a right mouse click, then selecting Touch. We can now browse the symbols of the DXC core by selecting the menu View, Symbols, Browse Functions. I will set an on-chip breakpoint on the DXC main function. I will restart the program execution. The target will stop after a short while at the breakpoint. We are now in the DXC phase. Trace32 allows to debug DXC drivers from the start. To do so, select the menu BLDK, DXC, debug DXC driver and enter the driver name, then press OK. Trace32 will wait until the selected driver is loaded and stop the program execution at its entry point. You can see from the frame window that the driver will be started. We can debug the driver now using single steps and breakpoints. Please note that debugging DXC drivers is even possible when no UEFI core symbols are available. We can display the list of loaded DXC drivers by selecting the menu BLDK, DXC, Display Loaded DXC Drivers. The debug symbols of already loaded DXC drivers can be loaded by simply doing a right mouse click on the driver, then selecting Load Symbols. I will now load the symbols for the boot device selection phase. I will then set a breakpoint at the entry of the BDS module by selecting the menu Break, Set, enter BDS entry, then type OK. Let's resume the execution. We can now debug the BDS phase. As you can see, using Trace32, it is possible to debug all UEFI parts and drivers from the reset vector up to the OS. This is all I wanted to show you in this video. The Trace32 UEFI awareness has, however, more features. For more details, I invite you to look at the following documents. Thank you for watching.